Dear students, welcome to Sri JCBM College YouTube channel, and today we are going to discuss another important concept in Laplace transform, and that is integration of Laplace transform or integral properties of transformation. So very simple concept, integration of or integral transformation, integral transformation So let us start with a statement of integral transformation. When a time domain function contain in a denominator t, it means so any time domain function f of t is divided by t, and how to solve the such a kind of problems, and we discuss with the help of the, or it helps integral properties in a such kind of concepts. So let us start with the statement of integral transformation, and as we know, Laplace transform of f of t is equal to f of s. So if you apply the Laplace operator on time domain function, we get f of s. This is a very basic definition of, we are already discussed in previous video also. Then Laplace transform of f of t over t. So this is equal to integration, limits values are s to infinity f of s ds. So this is the statement of the integral transformation. When a denominator is t, contain denominator t, and how to solve the, or how to find out the Laplace transform of such a kind of examples. So proof, very simple proof. So with the help of the definition of Laplace transform, we can prove this condition or this statement. Proof. So we have, or we know that Laplace transform of f of t. So basic definition of Laplace transform, that is 0 to infinity minus st f of t and dt. Also we call f of s also. Clear? And we call equation number 1. So this is the definition of Laplace transform, and we are already familiar with this definition. So by taking right hand side term, by taking this term, and we have to prove the f of t over t. So let, or consider or let integration. So just take condition of this one, integration s to infinity f of s ds, and we know that the f of s, we have already f of s with the help of the definition. So definition says that our f of s, just substitute f of s here, integration. So keep this integration as it is, s to, limit values s to infinity, and f of s is, this is whole thing our f of s, whole thing is our f of s, integration 0 to infinity e to the power minus st f of t dt and this ds. Clear? Just I substituted f of s here with the help of the condition 1 or equation number 1 from 1. by changing the order of integral or integration. Here we have to integrate, here we integrate s variable. So by changing the order of the integration, I rewrite the above condition. I'll take here 0 to infinity, because we are integrate with respect to s means we have to take the integral term inside and we integrate s terms. Where is the s? E to the power minus st is there, just we have to integrate e to the power minus st with respect to s. So I will take 0 to infinity, integration 0 to infinity and f of t, because we are integrating with respect to s. So only s terms integrate. Here I write f of t integration 0 to, not 0 to, s to infinity e to the power minus st and ds, by changing the order of the variable of integration. So bring ds inside and keep dt outside, just we are integrate e to the power st with respect to ds. So remove this integration by integrating and rewrite integration 0 to infinity, and this is our f of t. Now look at here. So integrate e to the power st. So we know that the basic formula of exponential of integration, and that is because we are observe here we are differentiating with respect to s. It means we have to partially differentiate s terms only, not t. So integration of e to the power minus st is e to the power minus st, and here the coefficient of s is t. Don't write s here because we are integrating with respect to s, and 0 limit values are s to infinity and dt. In next step, apply the upper limit and lower limit. These are the variable of s. This is a variable of s, means s is equal to s only and s is equal to infinity. So that is equal to integration 0 to infinity f of t. Look at here, apply the upper limit value e to the power minus infinity, and just substitute s values. S is equal to infinity and s is equal to s only, and denominator term is minus t and minus e to the power s is s only, and here st and minus t and dt. So look at here, e to the power minus infinity value, it means 1 over e to the power infinity. It means infinity, 1 over infinity is nothing but the value of 1 over e to the power infinity value is 0. This is a 0, and remaining 0 to infinity f of 2 and minus of minus plus this is 0, minus of minus is plus, and e to the power st divided by t and dt. So I rewrite this one, e to the power minus st f of t divided by dt. And now look at equation number 1. So which is looking like our definition of Laplace transform. We can write with the help of the definition of equation 1. So Laplace transform of f of t over t, and this is the proof of the given integral transformation, and it is useful in evaluating the improper integrals. So now we look at one of the example on the basis of integral transformation. Find Laplace transform of examples. Find Laplace transform of sin t over t. So if you know the condition of integral transformation, we can easily solve. Just remember the condition of integral transformation. Very simple proof. So this is in the form of Laplace transform of its integral transformation, that is we proved that is f of t. So our f of t is a sin t and t remains as it is. Okay. So just by taking f of t and apply the Laplace transform on f of t, and we get the answer in frequency domain, and after that apply the integral transformation. Solution, very simple solution. Let f of t is a sin t. If you compare with the condition of integration, means f of t is sin t. And now apply the Laplace operator on both sides. And that is Laplace of sin t. So we know that Laplace transform of sin at, general condition of or general signal of Laplace transform, and that is 1 over a square plus 1, and also this is our f of s. This is our f of s, because f of t is a sin t. If you apply the Laplace operator, it means we get answer in frequency domain, that is our f of s. We have, it means integral transformation condition, that is we have Laplace transform of sin t over t is equal to, it means just I write general statement of the integral transformation. Laplace transform of f of t over t is equal to integration, limit values are s to infinity, and f of s ds. Clear? So we have the condition of integral transformation. Just substitute the values here, f of s, whatever we get the condition or frequency domain of the f of t, just substitute and integrate with respect to s. So integration s to infinity, f of s is nothing but 1 over a square plus 1 and ds. Here f of t is sin of t over t. Now look at this one. So integration of 1 over a square plus 1 with respect to s means, so we know that the general definition or formula for the integration, that is integration 1 over x square plus 1 dx, that is tan inverse of x. Just apply this formula here and we get here tan inverse of s, and limit values are s to infinity, and apply upper limit and lower limit, and what we get. So here if you apply the upper limit, s values are s and infinity, tan inverse of infinity minus tan inverse of s. Clear? Upper limit minus lower limit. Next step, as we know, the tan inverse of infinity, for what angle we get? So tan inverse of infinity for what angle? So maybe 90 degree, otherwise we call tan inverse of tan pi by 2, it means tan inverse and tan get cancelled and we left pi by 2. So tan inverse of infinity value is, angle is pi by 2 and tan inverse of s, and also we can write this one cot inverse of s, because basic formula of the inverse trigonometric conditions, that is tan inverse x plus cot inverse of x is equal to 90, and we get the cot inverse of x. Otherwise we can write in the reciprocal form tan inverse of s, and this is also answer and this is also answer. So whatever it, so therefore Laplace transform of sin t over t is equal to cot inverse of s, and this is the answer. And such kind of examples are the integral transformation when denominator t is there. Clear? So we go to the another example on the same basis of the integral transformation, and find the Laplace transform of sin square t over t. So another example for the integral transformation, find Laplace transform of sin square t over t. So same, which is looking like the our integral transformation, because t term is in denominator and we have to compare with the condition or statement of the integral transformation. So solution, very simple solution. If you know the basic conditions of trigonometry, or easily we can solve it. So I consider very simple solution. Here let our f of t is equal to sin square t. Clear? We have to compare with the integral transformation of the statement. Now observe here, this is our f of t sin square t. If you apply the Laplace operator on both sides, we cannot be get the answer for the sin square t, because we don't have the standard signal for the sin square t, and we, for that purpose we have to simplify it as in a simplest trigonometric formula, and that is 1 minus cos of 2t over 2. This is the sin square t of sin square t, it means 1 minus cosine of 2t over 2. So now apply the Laplace operator on both sides. Laplace transform of f of t, and I will take 2 is common, 1 by 2 is a common, and Laplace transform of 1 minus Laplace transform of cos of 2t. So 1 over 2 and Laplace transform of 1, any constant value of Laplace transform is 1 over s, and Laplace transform of cosine of 80. So compare with the general or standard signal of the Laplace transform, that is cos of 80. So s over a square plus 4. Clear? And this is our f of s also. So Laplace transform of f of t. Now we have the integral transformation property. We have integral transformation property, that is Laplace transform of f of t over t is equal to integration s to infinity f of s ds. Clear? This is the general statement of the integral transformation, because given condition or given problem is in the integral transformation, because denominator t is there. Now therefore Laplace transform of f of t is nothing but sine square of t over t integration s to infinity, and f of s is, this is our f of s, that is 1 over 2 1 over s minus s over s square plus 4 and ds. So now integrate the terms. In next step I will take 1 over 2 t, 1 over 2 take outside, and integration s to infinity 1 over s minus with respect to s, and again integration, just apply the integration terms on both side, on both the terms. So here limit values are s to infinity and s over s square plus 4 ds. And now look at this 1 over s, because we are integrating with respect to s means 1, suppose we are integrating with respect to x and 1 over x is there, we know that we are already familiar with such a kind of integration, and that is 1 over integration of 1 over s is log s and minus and now look at here, it is also, so which is looking like integration of f of t, f prime of t, it means we get log of f of t. So basic formula of the integration. So here if you differentiate this term, we get the numerator terms with respect to differentiate this one 2s. So 2 is not in the numerator, so just we have to multiply and divide by 2. It means, so here multiply by 2 and divide by 2. So we get 1 over 2 log of a square plus 4, and limit values are s to infinity. So with the help of the logarithmic properties, we can write this one log m minus log n. So log of s divided by square root of a square plus 4. So 1 over 2, it means when I apply the logarithmic property, m of log n is nothing but this goes to the in the power form, it means 1 over 2, it means square root of a square plus 4. So if you apply the log m minus log n, we get the in the fraction, in the yes, we get in the fractional form, it means s over square root of a square plus 1, and limit values are s to infinity. Now apply upper limit and lower limit and we get the answer. Suppose here if you apply the directly upper limit value as a s as a infinity, s is equal to infinity, s square is infinity plus 4. So here we have to observe this condition is in the form of the improper fraction. So when the condition in improper fraction, and just we have to take the variable common, and after that, after taking the variable common, just after that we have to apply the limit values, and that is the procedure for the or properties of the limit. So here I will take 1 over 2, otherwise another step, limit of s as infinity upper limit value 1 over 2 log of s square root of a square plus 4 and upper limit value is, and that is so I write here square root upper limit value is 1 over 2. When you lower limit values, when you apply the lower limit as s is equal to s, means it gives the same answer, same that it itself is our answer, that is log of s over square root of a square plus 4 when you apply the lower limit value. Clear? Now, so if you apply the s as the infinity, because this is improper, which is in the improper form, and we take the variable terms as a common, after that, after taking the common, we have to apply the limit values for that. So write one more step here, limit of s to infinity 1 over 2. So now log of, so numerator is s, I will take a common s square from the square root of, then we get s and square root of 1 plus 4 over a square, and it is remain s over square root of a square plus 4. And now this s get cancelled, and now apply the limit s as a infinity, s as a infinity. Dear student, please observe here. So this s and s get cancelled, and here 1 plus 4 over s square is there. When you apply the s as the infinity in this condition, so 4 over s square, it means infinity square, infinity only, 1 over infinity value is 0, 1 over infinity value is 0, square root of 1 plus 1, 0 is 1. So we left here in another step. So 1 over 2 log of 1 square root of, because s get cancelled, 1 plus 4 over infinity, and minus 1 over log of square root of a square plus 4. So 4 over infinity value is 0, square root of 1 plus 0 is 1, square root of 1 value is 1. So 1 over half log, so I will take again 1 over 2 and 1 over 2 take common, so log 1 log of square root of a square plus 4. So again apply the property of the logarithmic property. So 1 over 2 log gives a square plus 4 divided by s, and this is the answer for the given Laplace transform of sin square t over t. So I hope you understood such kind of examples on integral transformation. Thank you, and we will see in some other example or some other concept in next video.